Welcome to the analysis and design of Cockcroft-Walton multiplier. This is the voltage multiplier circuit. As we have discussed in our previous lecture that the working of this Cockcroft-Walton multiplier circuit, how it works, and we also discussed the practical aspects of Cockcroft-Walton multiplier circuit. Here in this lecture we are going to study the analysis and design of the Cockcroft-Walton multiplier circuit, and this is the practical analysis and the practical design. So this is a very important lecture, and you must be with me along with this lecture, and we will be discussing very crucial important practical design concepts and analysis knowledge which is very limited in the literature available across the web. So let's start with the analysis first, and then we will proceed to the design example. So here you can see, here we have the circuit diagram of the Cockcroft-Walton multiplier circuit. If you are not familiar with this circuit, or if you don't know how it works, please refer to my previous video lectures. Here in this video lecture we will be starting from the ahead. Okay, so this is the Cockcroft-Walton circuit. Let's first draw the waveform, the practical output waveform of this circuit, and now I am going to remove this circuit diagram from here. And we will be starting from the output voltage waveform. As I told you, and you are well aware from your previous lecture videos, that we output from this Cockcroft-Walton multiplier circuit, theoretically it is equal to 2 times the number of stages multiplied by the V maximum. V maximum is the peak value of the input AC power source, n is the number of stages, and 2 is the multiplier factor. So practically this value is not possible. Why? Because we have the loading effect. You have to connect the load across the Cockcroft-Walton output. So let's have the understand. We also in the previous lecture we discussed about the waveforms, or about the equations which were telling us the information about how much maximum voltage we can achieve. Here in this lecture we are also going to cover that, a little bit of review, and then we will be proceeding towards analysis and design. So this is the generic waveform. Since, as you know, that in the Cockcroft-Walton circuit you have rectifier effect, you have diodes, and you have AC power source. So it's all about the rectification. So the output waveform, so at the output we have the capacitor, and that capacitor obviously is about to discharge across the test object. So output voltage waveform will be like in this fashion, like it is it has increases, decreases. It depends on your the test object. Like it will not be like exactly the sinusoidal. So it is not the sinusoidal, it has some value, and here is the output voltage waveform. This is V out, it can be in kilovolts. So this is, and what we stated that theoretically the V output is equal to 2 n V max. So we say that theoretically the value is this, which is 2 n V max. Now what is V max? You know, this is the peak value of the input AC power voltage. Okay, so now this is the charging and discharging behavior of the output capacitor, and this is the 0 value. Okay, and this is the voltage waveform. Now this maximum possible value, this is what the V max, this is known as V out max. Let's say this is V output maximum, and this is the practical output value which we are going to achieve when you connect a load. And now the difference between this theoretical voltage value and the practical maximum voltage value, we will say this is delta V out. Okay, this is what we told you in the previous lecture as well. This is known as the voltage drop. This is the voltage drop which practically you have to face in the Cockcroft-Walton multiplier circuit. And another, we can see that this is the peak and this is the maximum peak and this is the minimum peak. So the peak to peak ripple value, it can be represented by 2 delta. So this is peak to peak voltage ripple. So this is the practical output waveform from the Cockcroft-Walton multiplier circuit. Let's say if you have V input is 220 volts RMS, so what will be the V peak of the AC source? Let's say we have the AC source which is of the 220 volts RMS. So what will be the V peak? V peak obviously 220 multiply under root 2 is equal to 311 volts. So theoretically, if you have only one stage, okay, so voltage here should be 622 volts. But practically what is going to happen there, because you have the supply frequency, you have some value of the capacitance, you have the load current IL. So these factors play a role in deciding what will be the voltage drop in actual and what is going to be the output peak value and what will be the voltage ripple. And let me write the equations, standard equations for the Cockcroft-Walton circuit, and how these equations are derived. This is not our concern for this undergraduate course, but if you are in the graduate studies, then there are various researches which help us in this derivation as well, and as well as the improvement in the Cockcroft-Walton circuit. Okay. So the first value, I must say, you can have this is V out maximum, this is equal to, this is understood, this is equal to 2n V max minus delta V, which is the voltage drop. And how we can find out this voltage drop? This voltage drop is equal to the load current divided by the supply frequency multiplied by the capacitor to 2 by 3 n cube plus n square by 2 minus n by 6. So this equation gives us this value for our Cockcroft-Walton multiplier circuit. And what is the equation for the voltage ripple? So this is twice of the voltage ripple. Obviously there will be some DC value which is also known as the mean value. We are not interested in this mean value indeed, because we are in the high voltage and we must be aware of, or we must know that what is going to be the maximum value. We are not interested in this V mean value, because if you are designing a rectifier in the power electronics, then this value is important. Here it's not important. Okay, so this value, the ripple, the peak to mean ripple, okay, delta V You can find out the mean in this way. It comes out to be IL divided by frequency into capacitor into n plus 1 divided by 4. N is what? N is the number of stages. Okay, now in some literature, instead of 4, when they derive this equation by taking another type of assumption, this can be 2, but in most of the literature this 4 is the value which is in the denominator is taken. So you will be keeping this equation in mind in your notes for further reference. Now another important two equations are other important equations are like these. An optimum. Now what is mean by an optimum we will be discussing when we are going to discuss the practical example. An optimum is equal to V maximum multiplied by the frequency multiplied by the capacitance divided by the load current. You know now what is V maximum? V maximum is the peak value of the AC power source which is powering up the Cockcroft-Walton circuit, and another value V output maximum which is depending on the optimum stages. This is the equation for the optimum number of stages, is equal to N optimum multiplied by 4 by 3 into V maximum. So keeping these equations in your mind and this concept of output waveforms, now we are going to solve one of the practical circuit of the Cockcroft-Walton multiplier. So there we go with the analysis of a Cockcroft-Walton multiplier circuit. We had a practical circuit in our lab, and it has the 10 number of stages, and the capacitors which are connected in each stage, the each value is 0.06 microfarad, and the supply frequency we have is 150 hertz, and the transformer which we are using to power up the Cockcroft-Walton multiplier, the maximum value or the peak value at the transformer secondary is 100 kilovolt, and the loading current or the current which test object can draw is the 1 milliampere. So in this this would be a circuit of the Cockcroft-Walton circuit which is designed for such conditions. So what is the voltage drop? First thing, what is the possible voltage drop? So you can use this equation for the voltage drop, which is actually delta V output. So our current is 1 milliampere, and frequency is 150 hertz. The capacitances of 0.06 microfarads are connected, and we have 10 stages, so 2 into 10 cube divided by 3 plus 10 square by 2 minus 10 by 6. So this voltage drop comes out to be 80 kilovolts. Okay, and since there are 10 stages, so what is the theoretical output voltage? Theoretical output voltage can be simply 2n V max, and if it is 2n V max, so stages are 10 and Vmax is 100 kilovolt. So theoretically we must get 2000 kilovolts. Okay, so and after the voltage drops, as few moments before we draw the output waveform of the Walton multiplier. What was that? Let us draw for this scenario as well. So this is the, is this visible to you? Yes, it is visible. Okay, so it comes out to be 2000 kilovolt, but the voltage drop is 80 kilovolt. So V output maximum will be 2n V max minus V drop. V drop is 80 kilovolt and this is 2000 kilovolt. So we will be getting the peak of 1920 kilovolt practically when we are going to have this loading current. So this is as I told you, this is the output waveform. The output waveform is like this. So this value is equal to 1920 kilovolt because this is much. So here is the voltage drop, which is 80 kilovolts. One more thing to calculate is the peak to peak ripple, and we have the formula for the peak to peak ripple. And what is that? Delta, and the ripple voltage formula is equal to IL divided by frequency capacitance into n plus 1 by 4. You know load current, which is 1 milliampere, frequency is 150 hertz, capacitance is 0.06 microfarad. So it comes out to be 3.05 kilovolts, and so obviously 2 delta V will be 6.1 kilovolt. So the peak to peak ripple is around 6.1 kilovolt. So this will be the possible output waveform of a Cockcroft-Walton circuit having 10 stages and the capacitance of 0.06 microfarad. And theoretically, if you have 10 stages, you should get 2000 kilovolts, but practically you won't be getting 2000 kilovolt. Now next is another most important concept, is that how much stages we can go for. If you have this value of the capacitances, if you have the load current of 1 milliampere and you have the input power source having the peak of 1000 or having the peak of 100 kilovolt and frequency is 150 hertz, how much the maximum number of stages we can make. Theoretically you can go for 20 stages, 30, 50, 100 stages, but practically we have the limitation. There is the maximum number of stages. If you go beyond that, instead of that the voltage will increase, the voltage will decrease. So what is that maximum number of stages we can go for, keeping capacitors, the load current, the frequency and the input value fixed? What are the maximum number of stages you can go for? That is calculated by this formula. N optimum is equal to V maximum multiplied by the frequency, capacitance and IL. For this case, let's find it out what it comes out to be. You know N optimum, sorry, you know everything. You know what is V maximum? It is 100 kilovolt, frequency is 150 hertz, capacitance is 0.06 microfarad, and IL is 1 milliampere. So N optimum comes out to be 30. It means for this scenario you can go for 30 stages at maximum. Practically you cannot go if you have this all these factors, all these things with these components, you cannot make 40 stages, 50 stages, 60 stages practically, because if you go beyond 30 stages, let's say you make 35 stages, then instead of you are going to increase the voltage, your voltage will get decreased, because this frequency is then not suitable. If you want to do that, you will have to increase the frequency. This is more economical. Instead of increasing the value of capacitance, you can double it up, but you don't go for the higher values of capacitance. Either you play with the frequency, and increasing the frequency of the supply voltage is yet easier, and this is what economical, and it is done practically as well. So if you go for the 30 stages, then what could be the maximum practical value you can achieve when you go with 30 stages is N optimum is 30 multiplied by 4 by 3 is a factor, and multiplied by V maximum is 100 kilovolts, and it comes out to be 4000 kilovolts. Now again, now clear out your concept. Here we had the power source having the peak value of 100 kilovolt. We chosen the capacitors of 0.06 microfarad. This is the loading current, depends on your test object, which is 1 milliampere, and this is the frequency, supply frequency we had. So before that we were using 10 stages, and with the 10 stages we saw that the practical value of the output voltage we were achieving was 1920 kilovolt, and theoretically it should be 2000 kilovolt. Now if we go with the 30 stages, then what should be the theoretical value of the voltage you can have? So it can be calculated by this factor, like 2 into 30 into 100, it comes out to be 6000 kilovolt. But we have seen that this is the optimum number of stages is 30, so the maximum value which you can achieve under this scenario is not more than 4000 kilovolt. So if you are going to increase either more stages, like if you add up, if you go for the 35 or 40 stages, you won't be making greater than 4000 kilovolts in this scenario. So here we have discussed the analysis of a Cockcroft-Walton multiplier circuit. We have seen what is the voltage drop, what is the theoretical maximum value, and what is the mean value, what is the voltage ripple. So I have here another practical example of the Cockcroft-Walton multiplier circuit, which is at the 50 hertz frequency, and the input voltage is 220 volts. Let's discuss that as well. Okay, so let's start the analysis of a more practical and easily buildable circuit of the Cockcroft-Walton multiplier circuit. Let's say here we have the voltage source which is having the 220 volts RMS, and we are going for only the single stage. So this is the capacitance C1, and here we have a diode D1, and then we have another diode D2, and the diode and the capacitor C2. So here we have only one stage, and if this is 220 volt RMS, so its peak will be 311 volts. Let's say this is V max. Okay, so and the value of the capacitor, so the capacitor, let's say this is the value of the 3 microfarad capacitor we are going to use, and this voltage source is having the 50 hertz frequency. This is available to you, and this is the 3 microfarad capacitor, and let's say there its voltage rating, the maximum voltage this capacitor can bear is about 1000 volts. So this is the 1000 volts 3 microfarad capacitor, the specification of the capacitor. I am just removing this 1000 volt because I don't want to get confused into what is the output voltage. Okay, 1000 volt was the rating of this capacitor, that how much voltage that capacitor can bear. Okay, so and here we have the load resistance. So let's say our the current which the load can draw is 1 milliampere, the maximum current which the load will draw, and the capacitors obviously are same, so this is also the 3 microfarad capacitor. So at no load, what should be the output voltage? V output at no load, and this is what the theoretical value, it is equal to 2 multiplied by number of stages into the V max, and it comes out to be, stage is only 1 and the input voltage has the peak of 311 volts, it comes out to be 622 volts. Side by side, let us also make the output voltage waveform as well. So this is what the expected value, which is around 622. This is the dot is not here actually, this is the 622 volts. That was the sign on mark on the board. So 622 volts is the theoretical value expected. So here we have only one stage. So what will be the voltage drop? As you know, the equation of the voltage drop, which is equal to IL divided by frequency into capacitance into 2 by 3, let me write it in this way, n cube plus n square by 2 minus n by 6. You know load current, which is 1 milliampere, frequency is 50 hertz, capacitors are 3 microfarad and n is just the 1. So the voltage drop comes out to be 6.66 volts. Okay, this is the voltage drop. Then what is the maximum possible output voltage in this case? Obviously it is equal to 2n V max minus this voltage drop, it is equal to 622 volts minus 6.66 volts, it comes out to be 616 volts approximately. So output voltage comes out to be 616 volt. This is the maximum value of the output voltage which can be reached. So how it can be represented here? Let's say this is the capacitor charging and discharging phenomena. So this is what the 616 volts, and here is the voltage drop. Okay, it's clear to you? Yes. So and another important thing is here, what is the voltage ripple? The voltage ripple comes out to be again IL divided by F into C. It comes out into n plus 1 by 4. And you know IL 1 milliampere, frequency 50 hertz, capacitance 3 microfarad, N is 1, so it comes out to be 3.33 volts, and the peak to peak ripple is just twice of that, because this is 2 del V and this is how much it is? It is 6.66 volts. Interestingly, it was also 6.66 and here it is also 6.66. They are not necessarily equal, but here in this scenario it is equal. So here we have analyzed that what should be the output waveform of the single stage Cockcroft-Walton multiplier circuit. One more thing, an important step, as I told you, what should be the maximum number of stages. Now this is once I have designed the single stage. Now I am interested that I can increase the number of stages. Why? To increase the output voltage. Now if I want to increase the number of stages, how much maximum number of stages I can achieve? I cannot choose those maximum number of stages on my will, that let me take 10 stages, 15 stages, 20 stages. No, this is the practical scenario. You have the limitations of the input frequency, you have the limitations of the capacitor charging and discharging, you have the limitation of the current, the load current. You have these constraints, so you cannot directly choose the maximum number of stages which you can go for on your will. You have to find out using this formula, and that is what an optimum is equal to V maximum multiplied by the frequency into capacitance divided by the load current. V maximum, you know, 311 volts, frequency is 50 hertz, capacitance is 3 microfarad, IL is 1 milliampere, so it comes out to be 6.8. So we will decide that you can go for up to 7 stages. You can make total number of stages, you can make up 7 stages. You cannot go for 8, you cannot go for 9 stages, because in that way you will not be able to increase the voltage. Rather, if you will make more number of stages than 7, then your output voltage will rather decrease. So what is the V output maximum you can achieve if you go for with the 7 stages? So it is equal to 7 into 4 by 3 into V maximum, which is what you know, which is, and this is 7, what 7 is, an optimum, and V maximum is 311. It comes out to be 2.9 kilovolts. So this, if you increase the number of stages, you can only achieve 2.9 kilovolt, up to 2.9 kilovolts. You cannot go beyond that. Okay, theoretically, again, how much voltage you can get if you make 7 stages? How much voltage you can make? Let's calculate it. It is 2 N, which is taken up 7, and Vp. So theoretically you can go for 4.3 kilovolts, but practically you cannot achieve more than 2.9 kilovolt. Now if I make 10 stages, which is not suitable because our optimum number of stages is 7. Let's say if I go for 10 stages, then 2 multiplied by 10 multiplied by 311, it comes out to be 6.2 kilovolts, which you cannot achieve if you have this value of capacitor and this value of the frequency. So what to do if you want more voltage? If you have 311 volts, if you have only these capacitors, then how you can increase the number of stages? The fact is that you should going to increase the frequency. Instead of increasing the capacitor, you increase the frequency. Here frequency is 50 hertz. You can use the inverters which only increase the frequency, either 50 hertz. you can increase up to 150, 200 hertz frequency, 500 hertz frequency. If you go for here, then obviously your optimum number of stages will also increase, and the output voltage which you want, you can also achieve more voltage from that. So all is the game of the frequency. Increase the frequency, it is an economical way if you want more number of stages. Okay, so this is what we have discussed, two main practical approaches of the Cockcroft-Walton multiplier circuit. Now here comes another part, which is the design. Now what's in the design? Now design of the Cockcroft-Walton multiplier circuit is, obviously people design it, but it's very difficult that if I say that that my output voltage requirement is fixed. Let's say I say that I want the output voltage of I want the output voltage V output maximum. I want this output voltage. Let's say I say that I am willing to get to generate 20 kilovolts. Okay, then what are the design constraints or considerations? What should be the values of the capacitance? What should be the value of delta V? What should be the frequency? What should be the input voltage V maximum, the peak value of the input voltage? What should be these values, and what should be the number of stages? So now this design is not very straightforward indeed. As you have seen the equations, you have seen the equation of delta V, the output voltage, the maximum output voltage, the ripple voltage. So using those equations, and by first choosing one of the few things, you can proceed with the design. Okay, so how to start? My requirement is that I am willing to get 20 kilovolts is my requirement. Okay, so what should be the frequency? The first thing to choose, to look for what is the V maximum available I have in my lab, in my industry. So V maximum is obviously available, like let's say I have 3.3 kilovolts available, or I have 4.6 kilovolts available. Whatever the V maximum you have, first you look for it. Then you decide what should be the delta V, and delta V is normally, let's say we take it in the value of the 10%. This is the huge, anyhow the 10% is the maximum acceptable voltage drop. Let's say this voltage drop is delta V. So what comes out to be V maximum theoretically? So theoretical, you need to calculate it that. Now what should be the values of capacitors you have to take in? So the capacitors we will what is the basic practical approach? Either you choose the capacitors in the microfarad or the nanofarad or in the picofarad range. You can use any of these capacitors, and in these ranges normally 3, 5, 10, 15, 20 micro, nano or picofarad values of the capacitors are commonly used. And what is the frequency? Now here comes the value of the frequency. You have to choose, you know what is delta V, and then you know what is my V maximum. So using those equations which we have discussed, you can calculate out the missing values. So in this way you design the Cockcroft-Walton multiplier circuit for any fixed value of the requirement, which is generally it's not an easy task. It is a complex, because you have to do several manipulations. You have to increase or decrease, check for the various values of the frequency. So what else we can do is that if you have this input voltage waveform, you choose the capacitor, you choose delta V, you have the frequency, then you can say that if you go for one stage you get this value, if you go for two stages you get that value. So normally analysis is converted into the design task, and this is the way if you start from the scratch. So when you have start from the scratch, you have to find to choose some values. Delta V, I have told you, it is the standard, you can take up to the 10%. So other values you may have practically. So this is what, these are the design and analysis of the Cockcroft-Walton multiplier circuit. Regards and thanks.